Can you hear me? Okay, thank you. Sorry. I was just going through the announcements, but you can hear me now, which is good. So last time there's a question about set associativity and resource augmentation. So to recap, the theorem from 1985 tells us that if you have a fully associative cache with LRU and a fully associative cache with the optimal algorithm, which has full knowledge of the future, if LRU has twice the cache size, it can approximate the optimal algorithm within twice the number of cache misses. So in other words, you can get a constant factor approximation in the cache misses with a constant factor augmentation. And this is one of these really cool techniques introduced back then. This is the first time that resource augmentation appears, which is the idea of giving an algorithm with less knowledge more resources in some way. In this case, cache size, but for other cases, for other problems, you can augment like time, space, other kinds of things. And somebody asked, those caches in that theorem are fully associative. Do we know anything about set associative caches and augmentation? And I said, I didn't, but I would look it up. And the answer is that it's actually non-trivial, which makes me feel less bad that I didn't know. So in a paper last year in SPA, which is a conference on parallel computing, there was this work on set associativity and resource augmentation. So you can remember from last lecture that set associative caches are parameterized by alpha, which is how big your set is. So that means like how many things can go into your set based on your tag. And given your alpha way set associative cache of total size k, and assuming that you choose your sets with a fully random hash function, which in practice is not totally true because you choose it based on your memory address and you just choose it on the high bits, but maybe you can approximate it with a totally random hash function. And normally with set associative caches, there's this trade-off in alpha. So if your alpha is bigger, it means that your set is bigger, which means that you have less conflict misses, but you have to take longer to search within your cache, within your set. And if your alpha is smaller, it's the opposite way. It's faster to search within each set, but you have higher chance for conflict misses because there's fewer things that can be held in your set. So basically, they showed this theorem, parameterized by alpha, and they show that for alpha, which is little omega of log k, if you have a set associative cache with some resource augmentation of, so they're comparing to this fully associative LRU cache, and with a little bit of resource augmentation compared to the fully associative cache, you can get an additive order 1 approximation with probabilities 1 over 1 minus 1 over poly k, where k is the size of the cache. And they show that for little o of log k, it's actually the other story. So your set associative cache is not within a constant factor of your fully associative LRU cache for some sufficiently long request sequence. And then they show some function, some theorem. If you can change your hash function, then you can get some constant factor approximation compared to LRU with augmentation. So this is like pretty dense. The main point is that it's non-trivial to prove something like this. Okay. So last class, we talked about tiled matrix multiplication. And again, tiling is this thing where instead of doing full rows and full columns at one time, you cut the computation up into blocks. And based on your block size, then you do your computation in blocks of smaller rows and smaller columns. And if you choose your block size correctly, then you can get much better cache performance. And where we left off last class was that this is great. It turned out that if you do some proving, you can get asymptotically optimal cache performance in terms of M and B, which are your cache parameters. But there's some challenges in tuning your cache parameter S. So this is one level of tiling, which assumes that you have like one small cache and one big memory. But in reality, we know that we have many levels. We have like L1, L2, L3, and so on. So you would need something much more complicated than this to get all the levels of cache. And then it becomes even more complicated when you have parallel things running in your cache at once. So you have shared caches. So your amount of cache is not even constant over time. And so tuning S is challenging. And the question that we left off last time was, can we achieve cache optimality with no tuning parameters, or ideally fewer tuning parameters that don't grow with the number of cache levels you have? Did everybody remember this? Does this make sense? Cool, thank you. Okay, so the way we're going to do it is through divide and conquer. And divide and conquer is this technique where you cut up your problem into smaller recursive subproblems. And this is matrix multiplication again. you have C equals A times B. And the way that this recursive matrix multiplication works is that you can formulate this C in terms of several sub multiplications, like A11, B11, which are your sub matrices here, A11, B11. And it turns out that if you do 4 recursive sub multiplications, and in addition, that you can get the answer, and then you can just recurse further down. So like this is now again another multiplication, and we apply the same recursion. So this is 8 multiply additions of n over 2 by n over 2 submatrices, where originally you had n by n matrices. So this is the code to do this. The base case is at n equals 1. So at n equals 1, you just do the thing that we did in the lowest level of the for loops, which is C plus equals A times B for some entry of A times B. And this is 8 submultiplications, where you just recurse down into your subcases. It turns out that in practice, you have to choose a higher base case size than 1 because of functional call overhead. And I'll talk more about that later. So this is the way that you choose the, I guess the indices in your matrix. So this is like 0, this is your halfway by row, this is your halfway by column, this is your halfway by row and column. So that's 1, 1, 1, 2, 2, 1, and 2, 2 respectively. Okay. So remember that last time we showed that with the 3-loop version and also with the interchange and tiling, the work was still theta n cubed, because for every entry you have to do, you have n entries in your C matrix, and for every entry you have to do n squared work, so that's n cubed. And this recurrence relation is 8 subproblems, and each one is half the size, and you have to do order 1 work at each level, or you have to do order 1 work at the bottom, just this thing. And that turns out that it's theta n cubed again. So the way that we do this is that we have this recurrence relation, 8 subproblems, each of them is half the size, and then constant work at each level. So you start with your recurrence tree, W of n, and you have 8 subproblems, and each of them is half the size. And again, that cuts into 8 others. So each one of these cuts into another 8 subproblems, now each quarter of the size. And you can keep doing that all the way down in your recursion. And the height of the tree is log n, because each time the problem is getting in half. So you started with n, and by the time you get to 1, that's log n levels of your recursion. And you can count the number of leaves. So there's 8 leaves per level of the recursion, and there are log n levels of the recursion. And if you, this is like how you solve logs, or this is how you solve exponents. If you flip 8 and n to the log 8 is n cubed. So there were this many leaves in your recursion, and each one single multiply n, so that's n cubed work. Okay, so that's the same as the looping version, so we didn't asymptotically add anything in terms of number of operations. So now we want to prove something about the cache behavior, and we're going to show that the cache performance, there's 2 cases. One is this base case in the recursion. We're going to do n cubed or n squared over b work if n squared fits in cache. So this is like the same argument that we're making in terms of tiling, which is that if you can fit one of your subproblems into the cache, all you have to do is bring the subproblem into the cache, and then you can solve it fully. So that's why it's n squared over b, and you don't have to count cache misses in lower levels of the recursion because you have brought them already into the cache. And other than that, if you're higher up in the recursion tree, again, there's 8 subproblems. Each of them is half the size, and each one is order 1 at each level. So the difference between this and the work recurrence was that you cut it off higher than like 1. You cut it off at n squared. You cut it off at basically n, which is the memory size. Okay. So again, we're going to do this recursion tree, but now for cache misses. And the only difference here is that the base case is going to be different. So again, we're going to cut it in 8. Again, so that was n over 2, this is n over 4. And the number of leaves is now different than previously. Previously, we had n cubed leaves, Now we still have this 8 log n, which is the height. So now the total height of this is not log n anymore, but it's log n minus, this is log of m root m. So like we cut off the recursion when n squared was equal to m, because m is your memory size and n squared is the size of your matrix. And this is just log of square root of m, which is like, you have n squared equals m, which is n equals root m. So you subtract that from your height, and now you can solve this again using the same trick that we did earlier, and this is n cubed over m cubed. So this is the number of leaves that you have in the recurrence tree. And so so to go further, you have the number of leaves, and to get the total number of catch misses, you multiply the number of leaves by the catch misses per leaf. And the catch misses per leaf was n squared over b from the original thing that we had, which is the submatrix, how much it takes you to bring in the submatrix. So this times n squared over b gives you n cubed over p root m, which is the same as the tiling. Yes?
Is assuming that the cache is like basically completely wiped between each of the leaves, or there's no like the ordering of the leaves doesn't matter at all.
The ordering of the leaves
ordering of
doesn't
that
matter.
Like whatever the one leaf puts a cache will not at all be used by using that.
Will not. The order, you have to respect the order of the subproblems in the recursion. Like the thing that I showed you earlier with like the recursive calls, that has to be followed. But from an analysis point of view, you can consider like every subproblem where subproblems are of size m as clearing the cache. Does that make sense? So yeah, so this gets you the same cache misses as tiling, but the cool thing about this is that we didn't need knowledge of the cache parameters. We didn't need m, like that is part of the analysis, but it's not part of the algorithm. Like when I showed you the recursion, that was just recursing down to the bottom in terms of the programming. Yeah, so that is cacheable these algorithms, and there's a whole class of them. This is just one. There's like the most famous one probably, which is for dense matrix multiply, but there's a whole bunch of them. There's a paper from like the 90s that introduces this, and now there's been like 30, 40 years of work in this area. The cool thing about it is that you can get a good cacheability algorithm gets asymptotically optimal cache performance without knowledge of cache parameters. So like you don't need to do tuning, you don't need knowledge of cache sizes, you don't need the cache line or the size of the cache, and it asymptotically optimally handles all the levels of cache optimally, because you can make the same argument that we just did for one level of cache, but for all of them. Because in some sense, like the recursion, when you cut it in half, tiles for all of them optimally in some way. And one thing that has been recently been worked on is studying these cache oblivious algorithms in parallel environments. So when you have more than one thing running in your cache, and when your cache size effectively changes over time. And some folks showed that those asymptotically and practically work better, or cache oblivious algorithms are asymptotically and practically better in those kinds of settings. So that's cool. Yeah, so that's cache oblivious algorithms. Does that make sense? So next I want to talk about so we did a lot of theory last lecture and this lecture, and I want to talk about how these models and analysis are going to work out in practice, and also how can we get more specific models than just like M and B, which are sort of high level parameters that are not relevant to any, that are like, they're on every machine, but they're very general. So they would change across machines. So yeah, so today's lecture is on practical matrix multiplication and the roofline model. And I hope they get to the roofline model, but we'll see. Okay, so I'm going to do practical matrix multiplication. This is the code that we saw before. The most naive version of this implementation is with 3 loops, I, J, and K, and you have one multiply add at the lowest inside. Okay, so we're going to run it on this machine. This is a C4.8x large from AWS, which is like a cloud provider, and it has this chip. It has this clock frequency. Each chip has this clock frequency, 2.9 gigahertz. and it has two chips, and each of the chips has 9 processing cores, and it has two-way hyperthreading, which means that every core has effectively 2 threads, like it can kind of do two-way parallelism per core, and it has 8 floating point units per core, so you can do 8 multiply add per core cycle, and then your cache size at 64 bytes. And there's some information about the cache size. So what is the peak performance that we could possibly get from this machine? Well, the clock frequency is 2.9 gigahertz, which is 2.9 times 10 to the 9 flops per second, or cycles per second, which ideally translates to flops per second. We have 2 cores, or sorry, we have 2 chips. Each chip has 9 cores, and each core has 2-way hyperthreading and 8-way multiply add floating point units. So this is like the best that you could possibly hope for. And if you multiply them all together, you get about 840 gigaflops. Yes?
What does two-way hyperthreading mean?
Two-way hyperthreading means you have one, it's like a software level construct. So you have 9 physical cores, but hyperthreading gets you virtual cores sometimes. So it can like interleave instructions on one physical core in parallel. Yeah, so that's why I multiplied it. So this is like a very best case scenario for what we could hope for. So we can start with a very initial implementation in Python. We set the side length to be 4096, and we initialize the matrices randomly, except we initialize A and B randomly, and we empty C. And now we start our timer, and we do these 3 loops. And we do this addition and multiplication. And we print the time. So we got about 6 hours for this matrix multiplication. Yeah, so one question is like, is this good? Is this bad? Should we keep going? Are we done? What do you think? Okay. Yeah, why?
Well, I mean, this is, it's the naive, thing that's not taking into account any like cache, parameters.
You can write it in C and like get speed up just because C is like it produces machine code.
Yeah. Okay. Good idea. So we're gonna do that. Okay. So just to go back to what I was saying earlier, we had previously calculated our peak, and we're gonna calculate how far we are from peak, and it turns out that we are way less than 1% of peak. So we would hope for better than this. Oh, yeah, and the way that we calculated how far we are from peak is that we calculate the total number of flops we have to do, and we know that it's empty. Okay, so first, as an intermediate step, we can do it in Java, and that brings us down to 46 minutes, which is way better than the Python implementation. And like you said, we could do it in C. And from C, we can go from 40 minutes to 19 minutes. So that's already almost 2x better than Java, and about 18x better than the Python implementation. So just by changing the language, we got almost 20x improvement. So like you said, why is Python slow and C is fast? Python is an interpreted language, while C is directly compiled to machine code, and Java is somewhere, not exactly either of these. So Java is compiled to bytecode, which is then interpreted, and then just-in-time compiled to machine code. So Java is somewhere in the middle of these two. So that's why the performance is also in the middle. So the way that interpreted languages work is that the interpreter, as you go down the lines of code, the interpreter reads each line and then interprets it as you go, and it performs the statement, and then it goes back to update this total state. And the cool thing about interpreters is that you can do high-level programming features that you can't do in lower-level languages like C. You can't do like dynamic code changes, but unfortunately, you have to pay for those in performance. Okay. Yes?
Just to recap, so basically to calculate the peak of the performance of the program, one slide back, we just divide the number of flops by the seconds, right? Or
yeah, so you analytically can calculate the number of flops you have to do for the matrix multiply, which is like 2n cubed, and you know what n is, so this is the number of flops you have to do, and yeah, exactly. So you know the time, and then you know what flops per second you got, and you know what is the max flop per second you could get, and that's how you do that. Yeah. And JIT compilers, like I said in Java, you can get some of the performance back. So when you first execute the performance, you interpret it, so you have to pay the cost. And some runtime system, it keeps track of how often you perform the various code pieces, and it can keep track of how many times, it keeps track of how many times you execute them. And if you execute them sufficiently frequently, you compile them down to machine code in real time, and then you can look up the machine code, and that part is faster. So, yeah, so that's why it's somewhere in the middle. You have to eventually get to the fast implementation, but after some iterations of the slow one. So like we were doing earlier, we can also interchange the order of the loops without affecting the correctness. So like we did last class, we had ijk, and then we swapped it into ikj. And that gets us asymptotically better cache performance. In the worst case, this initial ijk version has n cubed cache misses. However, if you interchange the loops, you can always get n squared n cubed over b, because you get spatial locality in b. And we can try a whole bunch of different loop orderings. And it turns out that there's this huge variation, even by this very simple change. You can get a variation by over almost about 18x by just changing the order of the loops. And again, this is because matrices are stored in row order, row major version. Like I said before, you have this rows in your matrix. Row major means that you can concatenate them into like a 1D representation. So this is the initial version, ijk, and it had running time of over 1,000 seconds. And so you get, this is just a visualization of how you access the matrices. For C, you access C in order, so you get spatial locality in C. For A, you also access it in order. So you can notice like K is the fast moving dimension here, because it's the lowest one. And so A, like the fast moving dimension in A is also K, so it moves one by one for good spatial locality. But unfortunately for B, K is the slow moving dimension. K is a slow moving dimension. And so you have to jump really far in B. And since N is 4096, then you're jumping 4096 elements apart. So you don't get any locality in B. However, when you switch K and J, you still get locality in C, the same access method. Now A is fixed, and you get spatial locality in B. So the time changes down to less than 200 seconds compared to the over 1,000 from before. And just for, I guess, completeness, if you swap J onto the top and then K and I, you get poor locality in all of them. And that's why you could get even worse. It's about 3,000 seconds. Okay. Yeah, and like in homework 1, we can also measure the effect using cache grind. So if you haven't started it yet, we use cache grind in homework 1 to measure the cache misses and the miss rate. And these are the different loop orders. And you can see what the running time here. And you can see the worst one has the highest cache miss rate, which is about 15%. And the best one, IKJ, is 1%. And there's kind of an interesting question, actually, on a discussion, which is like, when you change from O0 to O3, your miss rate might actually go up. That's what they observed. And the reason is because the total cache misses is similar, because you still have to incur all the cold misses in this version, but the total number of refs you have to do is fewer, because you get like vectorization, so you have to issue fewer instructions. So hit rate is calculated, miss rate is calculated by misses divided by refs, and the other way, hit rate is hits divided by refs. And so if you decrease refs, both of them will go up. Yes.
If we quickly go to the slide back.
Yeah.
So, quick question. Basically, when we don't have spatial locality, does it mean that on the hardware level, we really have to go cell by cell, so to say, from one point from matrix A where the number is stored to another? Is it the case or not?
Yes. Yeah. So in this version, like from JKI, now for like when you're looking at A, K is the fast moving dimension, and then, but that's like higher up than I, so you're traversing down in A.
No, what I mean, for example, we have like this in-memory layout for the C measures, right? And there are some marked elements that we access in the memory here for the C. So the question is whether when we access first element and then access the second element, do we have to also traverse the whole memory block in between or not?
Oh, you mean like here?
No, right. Like, yeah, exactly. Do we traverse the memory block between or not?
No, we're going to jump from the memory block.
Okay, yeah, that leads to another question. How exactly then do we utilize the space locality if in both cases we know how big the jump should be, right? So when we have space locality, that means the jump is one, right? So like we just do a step. And here we do, I mean like a bigger step, but we always know the size of the step, right? So why in space locality case is it really that much faster?
Because you store when you access something, the operating system will take whatever, like 64 bytes or whatever, and put all of that in the cache because it knows that, or because it assumes that you'll be using space around it. So you'll already have that stuff in the cache. But here, you're not gonna, if you access that one element, you're not gonna have something 4096 down the road also in the cache.
That's what the lines are, I think. Like the line between each elements show like the ends of like what would be in cache, because there's usually some alignment to it. It's like when you access the first element, everything within that will be already in cache, so it would be
okay, yeah. Okay, yeah. But
Exactly.
Now I got it.
Yeah. Thank you. Okay, so yeah, so we're doing this interchange, and this is, yeah, so we can measure the cache miss rate, and in this case, cache miss rate corresponds to the performance. Lower cache miss rate is better for performance because of memory latency and time. Yeah, and I was just talking about something subtle, which is like the cache miss rate as a percentage may not be always super accurate because you have to look at both the total cache misses and the refs. So like if your cache miss rate increases, may not necessarily be because your total cache misses increased. So we did that. We did the interchange of loops, and now we got the performance down to about 170 seconds. And so what else can we do? Oh, sorry, there are questions? Hold on. The question is, when we calculate peak flops, why do we consider hyperthreading? Because hyperthreading doesn't change the physical functional units. Maybe that's true. Maybe it should just be multiplied by 8. Okay. Okay. So another simple thing we can do, in addition to loop interchange, is doing optimization levels. So we experiment a little bit with this in homework 1. But there's several optimization levels that are available in the compiler. There's O0 up to O3. And O0 is the least level of optimization, and O3 is the highest one. And we can try them all. And in this case, it turns out that O2 is the best one. And the reason that O3 is not always the best is because because O3 turns on all the optimizations, and it's not necessarily true that all the optimizations help you for every algorithm. So it just happened in this case that the optimizations that were turned on by O2 happen to help this algorithm the most without the additional overhead of the other optimizations. And yeah, and you can also do other optimizations like OS, which limits your code size, and OG, which is debugging symbols.
Oh, so you can do like your own specific individual optimizations. You don't just have to do like a more general O1 or O0 through O3. You could do specific optimizations if you want.
Yes, yeah. For example, like I'll talk about it later, but like one example is like with vectorization. You can pass in like mrg equals native to turn on vectorization.
Let's see, you can also write your own like list of optimizations to do in what order, because like O3 probably does most of the same things in O2, but it probably does it multiple times, because that's like optimization ordering is a big thing. So I think like Uber, for example, they had something where they found out removing 1 or 2 passes and adding like doing some other passes a few more times reduced the size of their app by like 80%. It's like the same like performance.
Yeah, for sure. Exactly. So like there's in addition to the number, just to recap, in addition to the optimizations performed, there's also the number of times that you perform them and the order in which you perform them, which is a whole other question and a whole other search space that the compiler figures out in these levels, but you can manually specify them if you want to. Yep. So when we turn on the optimization flags, we can get down from 177 seconds to 54 seconds. And with these small changes, like this is just changing the language and changing the loops and adding O2, we can get much higher performance than we originally did with Python. But we still have fewer than 1% of the peak performance. And why is that? Well, we've been talking a lot about caching. So, I guess first we can do parallelization. So we have parallelization. Actually, parallelization is the easiest to talk about in this case. But okay, so we have 9 cores per chip, and we have 2 chips. So ideally, we want to use them all. We are only using 1 so far. So many parallel programming language like OpenMP, Silk, TBB allow you to have parallel for loops, which let you execute the loops of the iterations of the loop in parallel. So here I just wrote parallel for. It's like agnostic to what underlying framework you use, but you can use anything. And this is IKJ because we did the loop interchange. And you can easily parallelize these outer loops I and J because then they write to other parts of C. But if you want to parallelize K, it's more complicated because then you would have multiple parallel iterations writing to the same location in C. And yeah, so these two can be easily parallelized. And one question is, which one should we parallelize? Should we do both? Should we just do one? You can experiment with it. So if you do just the outer one, you get 3 seconds. If you do just the lower one with J, you get over 500 seconds. And if you do both, then you get about 10 seconds. And in this case, the implementation happens to be in Silk, but you could implement parallel for in any of these languages. And this tells us that as a rule of thumb, it's best to parallelize the outer loop. And the reason is because when you parallelize the inner loop here, this part is still serial, which is, so this part is still serial, and there's a lot more, like how do I explain this? When you do parallelization, you want to have sufficiently large work per iteration because there's overhead to launching parallel threads. And so the issue with this is that you don't have enough work per iteration. So that's why you want to parallelize the outer loop.
And so what is for parallelizing like the outer loop and the inner loop?
Mm-hmm.
Is it just there that like, from like 3 to 10, maybe that's like not enough work to justify for like parallel, or for parallelizable tags to justify the overhead in creating the
Yep, exactly. Because when you do both of these, like the work per parallel task is just basically like this, which is not enough to amortize like the work of forking off a task and stuff like that. So yeah, there's this weird balance when you do parallelization, which is like you want enough parallelism, but you don't want like too much parallelism, because then if you just have a tiny bit of work, then it's not worth spawning it off into another thread.
I'm wondering, how does nested parallel work? Does it
How does
create a pre-structured thread?
Yeah, so one way to implement the parallel for is with nested parallelism. Like if you have n iterations, you could fork off like the first half and the second half recursively.
I'm asking the last one because we have nested parallel thread in one thread, and we will run into another parallel for. So we will create another group of threads.
Yes.
Create a pre-structured thread. Oh.
Yes, but you may have to do that even here because you can note that this parallel for is up to n, and you have more, like n is bigger than the number of threads. So you already here have more tasks than threads. So you have to figure out some way of assigning the tasks to the threads. And one way to do that is through binary forking. Does that answer your question? Maybe like there will be a full lecture on parallelism. So maybe if I don't answer your question by then, you can make sure that I answer it. Okay, so we do the parallel loops on the outer loop, and you get almost 18x speed up compared to the serial version. And this was really easy to do the parallelism. We just added one parallel for to the outer loop. Not all code is this easy to parallelize, especially if you have conflicts in writing, like I was talking about. And this is still about 5% of peak, which is much better than what we started, but not ideal. And yeah, so the reason that it's so low is we've been talking about caching for a while, so I don't want to talk about this in depth again, but this is just a recap. We have fast memory and slow memory, and we have cache line length, so we can take advantage of spatial locality, and we have cache line size, so we can take it, we have cache size, so we can take advantage of temporal locality. And there's cache hit and cache misses, and we want to increase the number of hits that we got. So this is some exact numbers, like concretizing the stuff that we were talking about earlier. So we were talking about cache performance in terms of M and B. How many memory accesses do we have to do to fully compute one row of C? So N is 4096. We have to write N times to C. And we have to read N times from A to read this entire row. And we have to read all of B. So that's 4096 squared. And this is the total number of memory accesses we have to do, which is almost 17 million to compute one row of C. Okay. But now we can do tiling. So how many do we have to do to compute this 64 by 64 block of C, which is equal in size, well, equal in length to one row of C. This is again 4096. So 64 times 4096 is this number of reads from A, 62,000, and the same from B, and the number of memory accesses is much less than without tiling. Okay, so this is the tiling code that I was showing before, this one level of tiling with the parallel 4 on the outside. And this is just a picture. We compute the subblocks, and we can experiment with the tile size. Since we have just one level of tiling, we have one fitting parameter. And just increase by 5 to 2, like 4, 8, 16, 32, and so on. And the best one is at 32 in this case. And we can measure the, so we can measure the cache misses again. And here we can see that the parallel loop implementation, originally you get 8,600 million misses in the last level cache with the loops. When you do tiling, you can decrease that to 416. So that is because of more cache friendliness in your tiling version. And so you can get, oh, and there's also fewer cache references. Yeah. So there's fewer cache references and fewer cache misses in the tiled version. And we just talked about divide and conquer. So we have 8 subproblems of n over 2 by n over 2 matrices, and you have to do one addition of n by n matrices. And this is, we just went through this. This is the code for divide and conquer matrix multiply. If you parallelize it, maybe this is getting at your question a little bit. So we had this one parallel construct, which is parallel 4 before. In addition, you can have parallel spawn, which is you have a function and you want to tell the underlying parallel library that it can execute in parallel with some other functions. And so that is what parallel spawn is. So this is telling us that these four can execute in parallel. These four can execute in parallel. And sync means that we have to wait here until all of these above have completed, and the same down here with parallel spawn and parallel sync. Okay, so initially we have this code, and this is the exact code that I was showing before. We have the base case, which is n equals 1, and you have parallel spawn and parallel sync. Initially, the runtime is almost 100 seconds, which is way worse than what we had before. And the reason is because the base case is too small, the same issue of having not enough work per parallel task. And so we have to coarse in the base case, which means make it bigger to overcome the functional call overheads.
Just a quick question back to tiling. So basically, when we have quadratic matrices, what we're trying to do is to minimize the number of cache accesses that we perform both for A and B, right? So, and when we deal with quadratic matrices, wouldn't be the tile number, optimal time number, always the same? Because I have a feeling not, but like from a logical point of view, it should be, because if we have quadratic matrices and then we have fixed size of those, then the size of tiles should be always the same.
Always the same, you mean like on that machine?
Yeah.
Yes, what does quadratic matrices have to do with it?
I mean, sorry, what was the question?
sorry, I think I didn't understand okay, so let me try to understand your question. So your question was that with quadratic matrices, is it true that like once you find S, it's the best S for any matrix?
Yeah.
Given the same machine and the same settings and so on. Yes, because S just tells you the size of the subproblem that you're solving. It doesn't matter like what the original size of your total problem was, because depending on the setting of S, you just get more or fewer tiles. I don't quite understand what it has, why it needs to be. I don't think it needs to be quadratic. Like they could be rectangular.
Yeah.
And it would still, you would just pick two settings. You can still pick one setting of S. Then the subproblem would show the same size. Pick two, but then now you'd have to try to co-solve two.
You still need a tune for each problem because the problem can be the taxes back.
For matrix
But I mean, like,
multiply,
if we have different matrix sizes, yeah, but if we have one matrix size, then
Just
it-
a matrix.
you
if we're limited to matrix multiply and on the same machine and with no like interference or anything like that, then once you find the right S, then you're good to go. Like it doesn't matter what the original size of your matrix, like the original size of the problem was, but yeah, I don't think it matters that it's square. It's just square because it's easier to do the divide and conquer when it's squared. And also power of two. Yeah, good question. So here we have this parallel spawn and sync version for the divide and conquer algorithm, and we have to tile, or sorry, we have to portion. But notice with portioning, now we only have one opening parameter, which is the size of the base case, rather than many, depending on the size of the level of cache that you have. And this is the base case algorithm. This is just the 3-loop version for simplicity with, yeah, and we just interchange K and J because we found that that was good before. Yeah, so we can experiment with the base case sizes, again with powers of 2. And here we find that the best one is 32. So this is 1.3 seconds. Yeah, so we had tiling before, which was almost 1.8 seconds. And then we have divide and conquer here, which is 1.3 seconds. So in this particular case, we found that tiling was worse than the parallel divide and conquer. But there's a bit of a caveat, which is like, this is not an extremely tuned cache oblivious algorithm, and that was not an extremely tuned tiled implementation. And there's been some study from 2007 showing that if you really carefully tune both versions, the cache aware version is better than the cache oblivious version because of, not just necessarily because of cache misses, but also because of like, because computers are not super well equipped to deal with recursive programs, and also because of things like registers. So if you want more details, you can read this paper. And yeah, actually, I wonder if this is still true today, because this is kind of an old study. But anyway.
It would make sense to me, because like, it would just, anything that like, if you can do like a bunch of tuning, it makes it that like, being aware of the cache is always better.
Yeah, I think so. Like if you know exactly your machine and you can tune exactly for the cache size, because like with cache oblivious programs, you're always like up to a factor of 2 off, because you're always cutting by a factor of 2. But maybe another way to say that, like on average, you're maybe up, you're not exact. You probably won't be exact.
Prefetches of any helpful?
Yes. Prefetchers are helping. They're not shown in tiling or divide and conquer because you already had. They help in the loop interchange because prefetchers help when you have spatial locality.
those are the hardware prefetchers.
Mm-hmm.
Can you put like explicit software prefetchers like say kettle and explore?
You can put them. Mm-hmm. They're not in this implementation, but you can put them.
Do they generally help?
Do they generally help? I actually have, in my work, have never found software prefetchers to help, but I wasn't trying to prefetch something so simple. Like for something like this, the hardware prefetcher is really good because you're just going forward. But sometimes, usually like when I'm trying to do software prefetching, I'm trying to prefetch like a pointer to somewhere else. And I never really found that helped me, but maybe I'm doing it wrong. Yeah. But there are software prefetchers. So, I have never tried using them on like sequential memory. Let me try it and get back to you. Okay, so another thing we can do is talked a little bit about this in the first lecture. So we also have vector hardware in our machines, which allows us to do single instruction, multiple data operations. So instead of doing one multiply add at a time, you can do a whole bunch of them. You load contiguous memory into your vector register, and then you do operations on all, you do the same operation on all the data that you loaded. Yeah, so you have a whole bunch of vector lanes. So that's what they call the parts of the vector register, and they operate in parallel on everything. You operate in parallel on all of the lanes. And each vector register can hold multiple words of data, which means multiple values. And yeah, so this is getting at the question earlier, like, can you, I guess we already talked about this, but can you turn on specific optimizations? There are a lot of these flags available in the compiler, like MAVX, MAVX2, which allows you to use these particular sets of vector instructions, AVX and AVX2. There's a whole bunch of other ones. Yeah, and I guess one subtle thing is that sometimes, because floating point arithmetic is not associative, you may have to add additional flags to allow the vectorization to happen. Okay, so if we use vectorization and we add fastmath, which is allowing us to do the vectorization, we can almost double the performance. Yeah, and yeah, so that was compiler automatic vectorization. We didn't add any code, we just changed the flags. And can we do better? You can manually do vectorization through things called intrinsics, which are these instructions that you could add directly into your code to do vector operations. And there's this website here that lets you look at all the possible instructions that you could use, sorted by the type. So this is like AVX, there's SSE, AVX2, and so on. So if we manually add intrinsics, we can, again, do a little bit better. We went from 0.7 to 0.4. And after all of this optimization effort, this version with all the things that we've done so far is competitive with Intel MKL, Math Kernel Library, which is a professionally engineered library from Intel. Okay. So this is like a caveat, which is you may usually not see performance improvements of like over 50,000 times, like we saw for this problem. Like we started with this very easy base implementation, and we did a whole bunch of optimization to get here. But however, in this class, we're learning these general techniques to try to improve a variety of applications. Okay. So that is all I want to say about matrix multiply for today. Are there questions?
Go back to the previous slide. Yeah, I'm wondering the difference between compiler vectorization and AVX intrinsics. Because if you can manually add some, I think they are assembly codes into your code, I think compiler can also do it.
Compiler can do it, but the compiler may not do it. Yeah. Like, I mean, clearly these two are different because if they were the same, the performance would also be the same. Why is that? If you add the intrinsics, maybe you're able to use like wider vector registers, or maybe you can do more efficient instructions, like a more efficient sequence of instructions. If you can think of like a smart way to do the vectorization.
This kind of tuning is very complicated.
Yeah.
We should better.
Yeah. Like better is probably to do like start with the things like loop interchange and like O3, and you can start with just turning on the compiler vectorization. And if you really feel like you need to go further, you can learn intrinsics, but it is really annoying to do the intrinsics. So if you could do other stuff like tiling or locality first, that's easier.
Or use the library.
Or use a library. Yeah, it's true. Like you could just, I guess here you could just call it MKL, but you may not have a library for all of your problems.
So
oh, sorry.
Intel's library for matrix multiplication. See, we were like, does it use like the same algorithm as base algorithm that is being used here, or does it use like a different or like a more fast matrix multiplication algorithm? Because I mean, here we didn't change like the algorithm that we were using, right?
Yeah, actually, I'm not sure. Like, you mean like subcubic matrix multiply, like Strawson or something like that?
Strawson.
Actually, I don't know. Let me look it up and I don't know if they would publicize what implementation
Yeah,
they would use.
maybe like it's possible that like maybe like Strawson is theoretically faster, but maybe in like doing all of these, it might not actually be faster because of this.
Yeah, in practice, I know like maybe you can get speed up with Strawson, but only like you should cut off the Strawson recursion at some point. Maybe after only like 1 or 2 recursion levels, you should switch back to cubic.
It could also just be better research too. Like if you run out of machine, they run really well because they make sure that spend a lot of time like going through this model.
Yeah, exactly. And they probably tune matrix multiplication really highly because like everybody's testing matrix multiply. But sometimes you can find that on like other machines or on other algorithms, the libraries are not quite as good.
So slides have the last level cache mentioned, right? So is the last level cache shared across all cores, or is it individual?
The last level cache is shared across the
So
cores.
each core has L1 cache and then one last level. So like if we have people memory, if we had L1 and L2 for a core and then a last level cache, like an L2 is last level cache, would that does that impact the runtime for matrix multiplication? Does it make it faster?
For this one, there is an L1 and L2 and the last level cache.
Because this is only
If there were
the last level cache, is there a reason we omit that?
Oh, cache grind does not show you the middle level cache misses, but there is a middle level because cache grind is not it's not actually running the code, it's running in a simulator. So they simulate only the highest level and the lowest level. It's probably, maybe it would take too much time to simulate middle levels also. That's probably why. But in reality, like when you run it for timing purposes, it is running on all the levels. Cool. Great. So we are finally done talking about matrix multiplication for today, and I want to talk about the roofline model for performance. So a performance model is a mathematical description based on a simplified machine model, ignoring a lot of details of the underlying machine that aims to come up with an estimate for expected performance. And so you take in these parameters like memory bandwidth and machine clock speed and memory footprint of your program and the total work in flops. And you hope to get like a performance number like runtime or energy use or fraction of peak. And notice that there's like a lot of stuff regarding your machine that is not considered in those things like bandwidth and clock speed. And the reason that we're interested in using performance models is because we want to predict performance behavior on a more fine-grained level than what we saw with the ideal cache model. So the ideal cache model just shows us speedups in M and B, but like it doesn't tell us exactly like a runtime number, or it doesn't tell us exactly how exactly what optimizations we should be doing. So performance models go one level more fine-grained than something like the ideal cache model, but still there's a lot of things that it leaves out, like the platform, like are you on AMD or Intel, or using C++ or Python, or OpenMP versus OpenSilk? Like these choices are all things that you have to choose when you actually do an implementation on a machine, but the performance model should be something higher level than that, like not to consider these exact details. Okay. So why are we interested in using performance models? They help us identify performance bottlenecks, and they tell us ideally where the bottleneck is, like is it in the software, is it in the hardware, is it in the algorithm, like what should we be optimizing? And maybe most importantly, like determine when we're done optimizing. How far are we from optimal, and can we hope to get closer to it? Okay. So the roofline model, the main idea behind it is that applications fall into 2 categories. They're either limited by compute peak or memory bandwidth. And so these 2 classes of problems are called bandwidth bound, which is limited by memory bandwidth, and compute bound, which is limited by your computation or like by your flops. And so for example, bandwidth bound is matrix vector multiply, and compute bound is what we were just doing, which is matrix multiply. And this model is from Sam Williams, who was a grad student at Berkeley when he first came up with this. The main components in this roofline model are, there's 3 main things. 2 of them depend on your machine. The first one is arithmetic performance on your machine in flops. So like we were doing this back of the envelope calculation before, it depends on your clock speed and how much parallelism you can get. Like we were doing the clock speed and cores and stuff like that. And it also depends on the memory bandwidth, which is the bytes per second. And we're ignoring latency for now. So this is the best case that you could possibly get. And so those are your machine parameters, 2 of them. And in terms of your application, we the bandwidth, or sorry, in terms of your application, the roofline model considers something called arithmetic or computational intensity, which is the flops per word or the flops per byte that your application does. So in some sense, this is like a measure of, kind of a measure of like how much work do you have to do per data moved. So that's why those are two extremes, like matrix vector multiply and matrix matrix multiply. Like for matrix matrix multiply, you have to do a lot of work per byte. But for matrix vector, you have to do way less work per byte. So that's why it's bandwidth bound, because you're dependent more on how fast you can move the data. And so depending on these factors, the roofline model tells us the maximum performance that we could possibly get for a given application. So this is what these plots usually look like. There's two axes. One is the max flops that we could possibly get. So this is your machine parameter, and this is your application parameter, which is the intensity in flops per byte. Okay. So we can, just like we did before, we can draw, this is just an example for illustration, we can draw the peak that we could possibly get in terms of flops per byte. And this is the roof of the roofline, which is the peak compute rate in flops. And so yeah, how good is it? Well, this is an example. That's the total number of flops you can get. For dgem, which is matrix matrix multiply, you can get very close to the top of the flops. But for this one, which is matrix vector multiply, we're way further down. Yeah, and this is the problem size. So why is that? Like, we were previously just using this one single number as peak, but why is this not really a good measure for matrix vector multiply? There's this concept of machine balance in your machine, which is the peak performance that you could possibly get in terms of flops divided by the peak bandwidth that you could possibly get in bytes. This is like, in some sense, yeah. So this is telling us like how many flops we can do, how many flops does it take us in terms of time to get to the bandwidth, which is bytes per second. And ideally the balance would be 1, which means like we can do 1 flop per byte moved. But usually it's much greater than 1 because, like I was saying in previous lectures, the clock rate is going up much higher than the memory bandwidth speed. Yes.
Why would it need to be like 1? Because a flop is going to be operating on like at least like a thing of size, maybe like 8 or 4 bytes. So would it be like? Maybe
no, that makes sense. If you operate on 32-bit, it's true, but like, it's not guaranteed that you could operate on smaller things like than 32 or 64. Like for example, in modern machine learning applications, there's a lot of work on doing like reduced precision in like 8-byte or 16-byte because of data movement. Like because they don't want to, because their applications are like limited by bandwidth, so they just want to move fewer bytes.
Yeah.
So the minimum, probably the minimum that you could possibly do usefully is 8 bits. Okay. So that's why it's byte. Yeah, good question. Yeah, so normally, so in machines, usually your clock rate is way faster than your bandwidth speed, and so the machine balance is much greater than 1. There's this other factor. So I was talking about computational intensity, which is just the flops that you have to perform divided by the data movement in bytes. So this is flops per byte again. And this is like a scale of intensity. On this side, this is sparse matrix vector multiplication. The intensity is super low. And on the other extreme, we have dense linear algebra. This is what we were just doing. This is dense matrix multiply. And somewhere in the middle is like FFT, which is like less than 2 flops per byte still. And for dense linear algebra, for sparse matrix vector, you may have like 10 or more flops per byte. So this is kind of like a way to determine whether you're bandwidth bound or compute bound, which is like, if you're here, you're probably bandwidth bound, and if you're here, you're probably compute bound. Okay. Yeah, so the roofline model tells us the max performance that we could possibly get. And assuming that we have ideal processors and caches, and assuming that we don't have anything yet in our DRAM, the max performance is bounded above by either the number of flops that we have to do or the number of bytes that we have to move. Like we are either going to be, yeah, so either we have to move this many bytes and we have to do this many flops, and it's going to take us at least like the longest one of these. And another way to say it, if you divided this if you divided this whole thing above by flops, like this is time, and if you did flops over time, then another way to say this is that you can do the min of your peak flops per second, or this is basically like your flops per byte. Okay, so again, this is an example. This is like a cartoon. You have this peak performance in terms of flops that we could possibly do based on the clock rate. And let's pretend that the machine balance was 4. Okay. So the way in the roofline that this works is that you draw a slope equal to the memory bandwidth from the y-axis to your peak line. And so this is like how much better you can do if you improved your memory if you like improved your locality. Yes.
Oh, where is it starting on the? Or wait, no, never. No, it starts.
It starts like it kind of like you can think of like drawing a negative slope based on the memory bandwidth from peak.
Oh, okay.
Based on like machine balance. So like you start from machine balance and then you draw the negative slope down. Yeah, and the slope is equal to the memory bandwidth. Okay, and yeah, so a balanced application is if you were at the machine balance and you had max bandwidth and you had bandwidth equal to flops. And otherwise, we have these two classes of applications that I was talking about. We have bandwidth-bound applications, which have low computational intensity, and compute-bound applications, which have high intensity. And so the roofline tells us what we can do in terms of software optimization for application and what we should be focusing on. Okay. So one thing we could do is if we are compute-bound, we can try to increase the peak. I guess another way to say this is, so the peak is like a very best case scenario. If you get SIMD and if you get instruction level parallelism and stuff like that, then you can reach like this truly best peak. But perhaps we are not getting there based on some setting of our application. Like if we're not taking advantage of all of these things, then the achieved peak that we can possibly get is lower. So one thing that we would focus on is trying to achieve these different optimizations. For example, we are doing explicit vectorization in the makeshift multiply example, and doing something like that can increase this possible peak attained higher than what we could possibly get from the compiler. And other ways to get this are like loop unrolling and instruction reordering and stuff like that. The second class of optimization is improving the attained memory bandwidth that we can get. So compilers usually don't give you good out-of-the-box bandwidth, so we have to manually do bandwidth level memory optimizations. So one way to do this is, so we want to increase the bandwidth ceiling. So again, like this, say this peak bandwidth is like the best case scenario that we could possibly get. But the effective bandwidth that we would see is much lower, for example, if we didn't do prefetching, or if we don't have NUMA memory control, which is like, in your machine, you have non-uniform memory access, which means that some memory is closer to some cores than others. And it's faster to access the closer one than the farther one. So if your allocation is not, or like if your allocation is not aware of that, or if your access is not aware of that, you may be reaching for the farther memory. So that's kind of going to decrease your effective bandwidth. So ways to increase your bandwidth ceiling are NUMA-aware allocation and access, software prefetching, and doing memory level parallelism. Okay. And prefetching, I think I talked a little about this before. Prefetching is this technique that fetches instructions or data from the original storage area before you need them. And there's two kinds. There's hardware prefetching, which is triggered by cache misses in cache lines, which don't necessarily have to be unit stride, but it's easiest if they are. And the software prefetching, like we were talking about, the compiler can insert instructions, or you can manually insert instructions into your program. Okay. Yeah. And then finally, another thing we can do to do optimizations is reducing the memory traffic. So this is what I was talking about before. Like one way to move from here to here is to like increase your computational intensity. You can either increase the flops or you can reduce the bytes. And so stuff like compression or like reduced precision are ways to move further along this way. So yeah, empirically, you might have this best case intensity that your program can achieve, but you might have much lower than your best case intensity. For example, like due to cache misses, you may be getting much fewer flops per byte because you have to keep accessing more data. And yeah, so one way to solve that is to pad your structures to reduce your conflict misses and use cache blocking, like use tiling, to avoid your capacity misses. Okay, so this is just what I was talking about earlier. Like, this is the very best you can get for peak if you imagine that you got all the possible optimizations of your machine. And similarly, this is the best you could possibly get for bandwidth if you got like prefetching and NUMA and stuff like that. So there's like this best case roofline, and there's also maybe what your application starts out with, which may be effectively lower because it's not taking advantage of the stuff in the machine. And so basically before optimization, you're only limited to like this small part. But if you do these optimizations, you can kind of like increase the possible range of peak that you can get. Okay. Yes, let me go back.
Quick conceptual question, not understand the roofline model. After we get to like a certain computational intensity, bandwidth doesn't matter anymore? Or, because like once we get to 4, right, we're not getting, bottlenecked by the bandwidth anymore. Or
Yes.
am I misunderstanding?
No, exactly. So once the intensity is high enough, you have reached like peak bandwidth, and then you're bounded above by compute. Like if you, sorry.
I think it's because in this case, like once you reduce 4 flops per byte, the bandwidth, the normal bandwidth without any optimizations is enough to get you like the peak. But if it was lower, then you would need to do more bandwidth optimizations to get greater performance. Like if you were at like 1 intensity, then not just doing like computational optimizations would get you there. You need to also do bandwidth optimizations. But if it's like 4, it just happens in this case that no optimizations on bandwidth would be required.
That makes sense.
Yes, exactly. Like I guess I won't go back further, but remember, like there are 2 classes of problem. There's bandwidth bound and then there's compute bound. And when you increase the intensity far enough, you're in compute bound, and that's kind of like you're saturating the memory bandwidth. And so you don't need to do further bandwidth optimization. You've already reached, you're now bounded by the flops, which are way higher. Thank you.
I don't get the meaning of the NUMA. Could you give more detailed explanation of the NUMA?
Yes. So basically, if you remember, even in the matrix multiply example, we had 2 chips, and each chip had 9 cores. It turns out that each chip also has memory associated with it. And so the cores can access memory from another chip, but it's going to take them longer to access that memory than to access the memory on their own chip. And if you're not aware of doing your allocation, or like if you naively access data, you may be accessing data farther away on another chip. Does that answer your question?
I don't know if I get it right. So if the matrix A is stored in the memory of the chip A, and now the chip A is doing a matrix multiplication, so I need to retrieve and copy the matrix A from the memory in the chip A to the memory of the chip B. So that multiply.
Yes.
Okay.
You may not need to copy, but at least you need to access. And so that is going to take longer. Yes.
If the prefetching is kind of like increase the computational intensity, because I can do more computation in the same period, so that I'm kind of increasing the computational intensity.
Prefetching doesn't improve the flops per byte. Like in some sense, at least it would keep it constant, because like in some sense prefetching increases your like bytes per second. Sorry. Yeah, so it wouldn't change your computational intensity, but it would change your effective bandwidth, because bandwidth is bytes per second that you can move through the controller. But in terms of flops per byte is dependent on your application. It's not dependent on the machine.
But what I'm thinking is that with prefetching, normally if I can't access the memory in a short period, I have to solve.
Yes.
But with prefetching, I can do more computation. Even if I can't access the data that I need, I can just skip this task and continue to do the other one, so that I can do more computation.
But
Could you say it again?
But operational intensity is measured by per memory. So like if you're just accessing memory faster, like sure, everything is happening faster, which is why you get high performance. But like if you're prefetching and you're accessing your data faster, it just improves your bandwidth, but you're still doing the same number of operations.
So prefetching is prefetch the data instead of doing the computational in the lab.
Yes, like prefetching just means that your data is available earlier, but intensity is like inherent to your problem or inherent to your program. Like, for example, for matrix multiply, like there's a fixed number of like multiply adds that you have to do per byte or per word or something. And that doesn't change with parallelism or prefetching or anything like that. It's like inherent to your problem. Does that make sense? Oh, sorry, we're out of time. Thank you. I had a couple of examples, but we'll do them next class. Thank you.